Good morning, ladies and gentlemen. My name is Istok Tissel. I'm a researcher at Josef Stefan Institute and professor of nuclear engineering at University of Ljubljana. And it's my pleasure and my honor to start the second day of the SCOPE-2 conference in Dhahran, Saudi Arabia. And it's also my pleasure to introduce two distinguished speakers that we have today. Each of them, our plan is like this, each of them will have half an hour for presentation, and then we'll sit together and we'll have quarter of an hour for discussion. So save your questions, write them down for the discussion at the end of the both sessions. And I will introduce our first speaker. This is Dr. Yong-hee Kim, who is currently a professor at the Department of Nuclear and Quantum Engineering of KAIST in Korea. He has a PhD in nuclear engineering from KAIST in 1995. His research interests include advanced reactor concepts and development of nuclear reactor analysis methods. He has extensive research and management experiences in the area of advanced reactors and reactor physics. He is a member of Korean Nuclear Society, American Nuclear Society, American Society of Mechanical Engineers. From 2013 to 2018 and from 2020 to 2022, he served as a member of Advisory Committee for National Safety and Security Commission of Korea. He's an editorial member of Nuclear Engineering and Technology journal and an executive editor of Progress in Nuclear Engineering from 2017 to 2020. When he served as a chair of the Reactor Physics Division of Korean Nuclear Society. Currently, he's in charge of Future Institute of National Strategic Technology and Policy at KAIST. So, Dr. Yong-hee Kim, the floor is yours.
Thank you very much, Mr. Chair, and very good morning, everybody. Looks it's too early. People are coming, but let me begin with the schedule. So, again, it's very big, pleasure and also honor to be here as a panel speaker to share some of the research outcomes in my group in my university. Today's topic is about my dream, actually. So we are working on a very sustainable and truly sustainable, I say, nuclear reactor system to address all big issues we have in whole nuclear industry, and so-called the trilemma. So possibly this can be provocative to some of you, but please understand this is a research work and we are just proposing a possible pathway to future nuclear. Can I go? Okay. So let me begin with the top 10 humanities problem. As you understand, the energy is the biggest problem and issue in whole world. And the global warming we have nowadays, making it more complicated and more challenging. And in addition, people say the global warming is triggering huge climate change. I'm not going to discuss this because I'm not an expert here, and also some people say this is quite controversial. But looks like the global warming is truly happening, and we have to worry about the climate change. So, in the middle of combating climate change and global warming, many countries are paying big attention to the nuclear energy again, announcing, for example, more than 30 countries are trying to tripling their nuclear installation. Tripling, not doubling. And more interestingly, the USA, they announced they will quadruple the nuclear capacity in the US only. This is a huge challenge, I believe. And believe or not, every year in China, they are adding about 10 big-size nuclear power plants to the grid. I say 10. So it looks like a nuclear renaissance is really coming again. And the European countries, they are returning to nuclear, well, except Germany. Hopefully, the Germany may also change their mind. And the big tax in all countries, I believe, but largely in the US, Microsoft, Amazon, and Google, and even Meta, they are investing a lot of money in nuclear projects and in nuclear, business areas for to develop the AI and also to construct the data centers. So it looks very, 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 promising. The nuclear is coming, but actually, I am questioning: are we ready for this big size expansion of nuclear in whole world? Frankly speaking, we are not really ready for this big size expansion in the near future. I believe we have to address, we have to solve the trilemma, the big issue in the nuclear industry. The first one, as we all understand, the safety. Well, we do have a wonderful safety record compared with the other energy resources. Nevertheless, we cannot emphasize safety too much in all nuclear sectors. And in some nuclear industry, including Korea, the spent fuel, this is an urgent issue. We have to do something to deal with the spent fuels. Unfortunately, in many countries, including Korea, we are just waiting for some solution to come. One good news is in Finland, they will possibly open the underground repository sooner or later, maybe early next year. But I think dumping the spent nuclear fuel into underground is not the best solution. There could be a better one, and I believe we can devise much better one. And the topic I am trying to share today with you is about that, actually. And if we add several hundred, more nuclear power plants in all countries, globally, then the uranium resource will become quite serious issue. Actually, we already recognize, the big issue in the resource limitation. On top of that, let me just mention the practical issue, the economics of nuclear. In all countries, possibly except Korea and China, economics of nuclear is not that good. It's quite bad, people say, and the general people, they complain about it. So, for sustainable nuclear, I believe the economics of the nuclear should be improved a lot. So, how can we address this big issue altogether? I'm trying to propose one possible pathway to solve them. And here I list up several sort of an attribute or requirement for truly sustainable, or personally I say ultimate reactor. First of all, it should be passively safe, or some people say the severe accident-free design should be done. And also, the spent nuclear fuel should not be accumulated anymore. And then the next one, we don't have to worry about the resource, including uranium and thorium. And of course, the economics should be much better than the current ones. And as always, there is no proliferation concern. Otherwise, we cannot expand a lot. And when we think about the climate change and decarbonization globally, then we understand we have to produce the hydrogen as well, not only electricity, because other than the electricity sector, the hydrogen is critically necessary to decarbonize. And possibly the nuclear reactor could be or should be autonomous, and then much more safer and economical. So we are proposing a liquid fuel molten salt reactor, actually molten salt fast reactor, to address all the issues I mentioned. So let me say why. Here you see some big motivations for the molten salt reactors. First of all, we understand and we believe it's possible to eliminate the severe accidents in the molten salt reactor simply because the fuel is liquid. For example, when something goes wrong very, very much, then we may drain the liquid salt fuel into very nicely designed systems, and then the decay it doesn't matter at all. In addition, if you recall the standard molten salt reactor schematic here, the liquid fuel is circulating in the primary systems. So removing the decay heat is much, much easier than in the standard solid fuel reactors. And there is no high pressure system here, and that is another big advantage of the molten salt reactors. And in the worst situation, for example, a lot of spill out accident, then we worry about the release of radioactive nuclide into the environment, for example, iodine and cesium. But please recognize and note, cesium and iodine, they are largely soluble in the molten salt. So they should, remain in the salt, even in the worst situation. And that is big, big advantage of the liquid molten salt reactor concept. And I have to mention, if you rely on the liquid fuels, we don't fabricate the solid fuel. That means there is no accumulation of spent fuels anymore. When you need some small amount of nuclear fuel, you just feed in. And then you can remove the unnecessary fission products continuously, online. So the fuel utilization could be ideally maximized. And the fuel is liquid, so if you think about the response when the temperature suddenly increases, then the volume should expand. And then, due to the negative feedback from the fuel volume expansion, the reactor should be, sometimes eventually subcritical. So the inherent safety should be very, very wonderfully good. And because of that, the expert and we say the passive safety is scalable, only in the molten salt reactor. What I mean is, in the standard solid fuel reactors, we need small modular reactor to guarantee passive safety. Because if it's too big, we may have to worry about meltdown. But in the case of liquid fuel, even with gigawatt, big size molten salt reactor, the passive safety is achievable. Yeah, it's a huge advantage. And also, its operating temperature is quite high, like more than 500 degrees. So the thermal efficiency should be much higher than that with the standard reactors. And also, we found that it can be autonomous. So possibly the economics could be also much better because of the passive safety and the very simplified reactor system designs. I mentioned a few good things, but obviously there is no free lunch, so there are challenges. And the biggest challenge is the material corrosion. We do need advanced materials. But I don't mean we cannot design, this kind of ideal molten salt reactor with the current available material. Yes, we can do, but the lifetime can be rather limited. And if you look at some advanced molten salt, like chloride salts, we need more knowledge about the thermochemical properties of the pure salt itself. It's ongoing research. And there are some concerns in terms of the proliferation, in terms of the operation. So we have to make sure the system design should be very much proliferation resistant. So with that, let me recall a milestone and crazy experiments people did about 70 years ago at the MSRD system in the US, Oak Ridge National Laboratory. So they built, as you see here, sort of an experimental molten salt reactor. It's 8 megawatt thermal. And they made the reactor prompt critical suddenly. I said prompt critical. And then the reactor power should skyrocket and suddenly increase. And they just wait. They didn't do anything to protect their reactor. And look at the response, in the right-hand side plot. The temperature increased, well, rather quickly, but it's bounded a lot. It doesn't exceed 700 degrees and gradually decrease. So that way, the molten salt reactor can survive super prompt criticality accident. This is actually one of the evidence of the passive safety nature of the molten salt reactor. There are a lot more, but I cannot discuss all of them today. The molten salt reactor is basically thermal spectrum reactor. However, if you recall the requirement I mentioned today, thermal spectrum is not a good idea because we have to make it sustainable. We have to make it, very, very effective in terms of the resource utilization. For that, it should be fast reactor. Unfortunately, some companies and some countries are developing molten salt fast reactor to achieve, very nice resource utilization. As you see here, at the bottom of the right-hand side, the Bill Gates, TerraPower, they are developing molten salt fast reactor without any recycling. It's a rather simple one. On the left-hand side, in the in the EU, European countries, they are developing big-size molten salt fast reactor, which may be recycling spent fuels. And in Korea, we are looking into this kind of advanced molten salt fast reactor. And for the molten salt fast reactor, we need a new salt fuel, which is chloride, not fluoride. Because in the chloride salt, the uranium solubility is much, much bigger, and then we can achieve much higher conversion ratio. And that means we can utilize the spent fuels very, very nicely. I will show you. So here you see a few, actually 3 chloride salt fuels. Some binary, the left-hand side and the right-hand side, and in the middle, a ternary or tertiary. So you may use NaCl, which is some table salt actually, and KCl and UCl3. And sometimes just the binary. So if you look at the table, the melting temperature is quite high. Above 500 degrees C. So that means, yes, you have to make it high temperature reactor. So in many molten salt reactors, the outlet temperature is almost 700 degrees C. This is very good temperature to produce hydrogen as well as electricity. And also that means when the the molten salt leak out to the environment, it should be solidified quite quickly and retaining all the fission product, as I mentioned at the beginning. So from now, I will show you our research outcome. We are working on molten salt fast reactor with a closed fuel cycle over the years. My student is just trying to publish in a journal. So this is the spent fuel we have in Korea. At the moment, we have 20,000 ton spent fuel, about 10,000 ton from LWRs, and another 10,000 from Canadian CANDO. And in the US, they have about 90,000 ton of, almost light water reactors. So let's think about the energy potential of 20,000 ton we have in Korea. If you convert all of this spent fuel into energy, I can say, you may easily understand, even calculate, it should be equivalent to the total electricity whole South Korea used over 300 years. I say over 300 years. We don't need any natural uranium anymore. And I believe in the US, it can be, that kind of big several hundred, energy resource in the whole US. It's really huge. Fortunately, in the molten salt fast reactor, yes, we can utilize all the spent fuel. All the spent fuel. So let me talk to you some details of our studies. This is just general comparison between open fuel cycle in LWR, so any kind of, and left-hand side, closed fuel cycle with a sodium-cooled fast reactor. We understand the resource utilization can be almost 100 times higher, well, at least 70 times higher. So over the 25 years in Korea, we did a lot of study about reutilizing the spent fuel in a limited sense using pyroprocessing and sodium-cooled fast reactor. The pyroprocessing is used to recover transuranics from the oxide spent fuels in a very, very proliferation resistance way. And as you may understand, pyroprocessing is high temperature electrolysis. So they say this is extremely proliferation resistance compared with the conventional Purex. And in the right-hand side, you see schematic how we reuse the TLUs, which is recovered from the spent fuel or PWRs. So first of all, we recover the TLU, but not pure TLU. It should be rather contaminated with a lot of uranium and even fission products. And it's going to be fabricated into solid fuel for the dedicated sodium-cooled fast reactor. And it's burned there. And again, as we understand, in any kind of solid fuel reactor, the burn-up cannot be high. Even in the fast reactor, it can be at best 20%. So we have to recycle the unburned TLU indefinitely. So because of that, it's not that simple. It's not that economical. And after some anti-nuclear government in Korea, this program was terminated, and we lost a lot of momentum regarding the sodium-cooled fast reactor because general public, they don't welcome. But I have to mention the pyroprocessing was developed in collaboration with the US. And it's going to be completed next year, and we understand it's quite ready for demonstration. So, in my idea, we do this way. The LWR spent fuels will be pyroprocessed. And this pyroprocessing will be very much, much simpler than the conventional one I just introduced a minute ago because we don't need pure TLU. we don't want just to incinerate the TIU. We will try to use this as the fuel for the break-even molten salt fast reactor. So the TIU fraction is only about 15%. This is necessary only for the very initial molten salt fast reactor. So that way we achieve initial criticality. Once we achieve initial criticality, we don't need TIU anymore because this molten salt fast reactor is going to be supposed to be break even. What I mean is, in the middle of operation, the fuel is self-generated. So we don't need any fissile fed from outside. Instead, we just feed a dirty spent fuel after reduction. And that is truly extremely proliferation resistant, pyroprocessing of the spent fuels. So in the middle of operation, we feed small amount of spent fuel, for example, 3 kilogram every day if the reactor is 3 gigawatt thermal, and we have to remove some of the fission product because to get to the equilibrium cycle, if you think about the mass balance, A comes in, then A should get out. So same amount of fission product should be removed. So this is the whole cycle we need and we have to carry out. So I believe the pyroprocessing will be really simple and could be proliferation resistance, and it can be quite economical. And let me just mention again, the pyroprocessing is necessary to achieve the initial criticality. So if you try to design several more this kind of reactor, you have to pyroprocessing some more spent fuels. And in Korea, as I told you, we have 10,000 PW spent fuels. If we pyroprocess that whole spent fuel, we can make about 3 gigawatt size this reactor. That is big enough, actually. So with this introduction of the molten salt fast reactor, this is the schematic we need in the pyroprocessing. So the spent fuel just first reduced. The reduction means removing the oxygen. And then in the electrorefining and electrowinning process, we recover largely uranium containing about 15% TIU. So this is very simple and I believe quite economically done. And with that, now let me show you schematics of the 3 gigawatt molten salt fast reactor we considered for these neutronic studies. So if you look at the reactor core, okay, we have a cylindrical about 3 meter diameter and same 3 meter height reactor core, surrounded by just the stainless steel reflectors. And outside the active core, we have an inactive molten salt fuel because it should be circulating. So it comes in at the bottom and get out at the top and goes through the heat exchange and comes back. So this way it's always circulating. And then the inlet temperature should be about 600 degrees C, outlet temperature about 700 degrees C. So, yeah, we have designed 2 initial cores, based on the binary or ternary. And then this is the just the initial core design. So if you look at the composition, the KCl takes about 46% and TIU about 9% in both cases, okay? And then the reactor diameter 3.3 meters. The initial inventory of uranium about 67 tons in both cases and 15 ton TIUs in both cases. Please recognize the rare earth is almost 8 tons and 9 tons. We do need this. So with this initial, now we will try to operate the reactor to achieve equilibrium break-even. So the starting reactor is not break-even. It's quite close to the break-even, but it's not very break-even. So you should, consider rather special strategy of operation. So to remove the fission products and to feed the fuels and also potassium and chloride. So with this kind of operational strategy, we achieve this kind of transition from the initial to the truly equilibrium break-even. So if you look at the top left, this is the excess reactivity. The excess reactivity will be less than or similar to just $1. And if you look at the top right and top, you see the conversion ratio. The conversion ratio is slightly over unity at the beginning and gradually approach to 1.01, which indicate it's going to be truly break-even. And then the safety parameters all perfect, strongly negative. And then the delay neutron precursor, yes, the fuel is circulating, so we have to consider the flow of the precursors, and we do understand there's some loss of the delay neutron precursor, but this is all manageable and doable. It's about the spent fuel recycling. What about, we have no spent fuels like Saudi Arabia and newcomer countries? Then you can begin with HALEU, the high assay, low enriched uranium. And then the difference is just in the initial core. So the initial criticality will be achieved using HALEU. And the necessary enrichment is only about 13 or 14%. And we do all the same way. And we got similar transition from the initial, core to the truly equilibrium molten salt break-even fast reactor. And then the safety parameters, well, the initial coerced uranium is slightly different, but all good in terms of the feedback. And the delay neutron precursor, again, slightly different between initial, but the equilibrium, but again, it's all doable and manageable. So with that, let me conclude my talk here. So I believe the spent fuel can be very nicely reused in the break-even molten salt fast reactor. And then the BMFR can be initiated with HALEU fuel if there is no spent fuels. So with that, I conclude the BMFR could be a strategic approach to address the trilemma or the big issues in the whole nuclear industry in the world. So with that, thank you very much for your attention.
Okay, thanks to our first speaker. As I have said, please write down your questions. The discussion will follow after the second presentation. And our second distinguished speaker is Professor Luis E. Herranz. He has a PhD from Polytechnic University of Madrid from 1996. He's a research professor since 2015. He has been leading the unit for nuclear safety research for more than 25 years. As a consequence of his research in national and international projects, he has published hundreds of research articles in refereed journals in the areas of severe accidents, nuclear fuel thermomechanics, thermohydraulics of passive safety systems, and power cycles in nuclear technology. He has been coordinator of some recent Euratom projects in the area of nuclear safety, and since 2018, he has been the leader of the technical area 2, this is severe accident area, of SNETP New Guinea. In the frame of OECD NEA, he was the chair of the W-Gamma Working Group of Analysis and Management of Accidents between 2015 and 2021. At present, he is a member of the advisory board of W-Gamma and the Working Group on Fuel Safety, and the expert group of small modular reactors. With a strong commitment to teaching and training, Luis E. Herranz directed the Master on Nuclear Engineering and Applications of Universitat Autónoma de Madrid for more than 10 years. He lectures regularly in national and international graduate and postgraduate courses on nuclear technology and nuclear safety. He has been collaborating for years in education and training seminars and workshops organized by NEA and IAEA concerning severe accidents and accident management. So this is also the topic of his talk today. Luis.
Good morning, everyone. Thank you for waking up earlier today. Let me try. Can you hear me? Soft? Can you hear me? Yeah. Thank you. Thank you. First of all, it's a pleasure for me to be here again. This is my third time in Saudi Arabia, so we are almost family here. And whenever I come here, I am very impressed for the evolution of your work, for the evolution of your infrastructures, and for all the things that you are building up in so short time. So congrats all the university, KFUPM, for your successes. But today, besides showing my gratitude to all of you, I want to talk about something quite different from the previous talk. And it's so good to talk about innovation. I mean, we have to. We are researchers. Many of us are. But it's very important not to forget about the past. In our recent past, compared to the human history, we got an event, the Fukushima accident, that even if it doesn't sound like very appealing, well, we got many things to learn from that. And we first started that long journey of learning years ago, right after the accident. But there are some things that we still don't know, but we can encapsulate already those lessons learned so that we are capable to make our nuclear power plants safer. So these are the contents of the presentation, going from the motivation through the forensic analysis, the ongoing investigation, just to land in the lessons learned today. Of course, just with the sentence that you got there is enough as a motivation. But you know, sometimes I talk to public, and then public say, well, right, Luis, then we got an accident, and why the hell do you want to keep on digging on that? So leave it in peace. And then I was forced to come up with something that is really hard to say. We've undergone 3 major accidents in our commercial nuclear power plants. Some people say 5. Okay, let's say 5. I prefer to say 3 for some reasons. So it's TMI2, it's Chernobyl, and Fukushima. So the point is just 3 real, actual, severe accidents. This is all what we got. This is all the data, real data that we got. And from that, we need to build up the whole validation and verification thing that you've been hearing about these days. So how can we go from an accident like Fukushima to make our MPPs safer? Because this is the challenge. So let me tell you what we did. Very early after the accident, our Japanese colleagues released some, what I call in the presentation, early data. And with those early data, mostly the industry did some early diagnosis. And based on those early diagnoses, they just build up immediate action. With immediate, that is in quotation marks, we mean in the range of 3 to 5 years. We implemented new features such as auxiliary equipment on-site, emergency centers somewhere in the country, new systems like the filter containment venting system, the passive photocatalytic recombiners in those plants that were not installed before, and of course, a full review of the accident management guidelines. And this was right away. But we did something else. That part, particularly on the research side, we did forensic analysis. And I will come to the point to explain with a forensic analysis, what we call forensic analysis, for the accidents in the 3 units of Fukushima that underwent the accident, unit 1, 2, and 3. So we came up with potential or postulated scenarios that could explain the data that we got at the time. But with time, further data came. And even now we are starting to get some samples. Of course, just few samples with minimum material. But this is helping us to still ongoing forensic analysis, because it's very important to realize that by having consolidated scenarios that can explain what happened in the 3 units, one of the things that we are doing is just testing how efficient those measures that we are taking quite at the early times after the accident would have been in the case of having them implemented there. First thing. Second thing, of course, with the methods that we use, mostly analytical tools, we help or we support some of the decommissioning and dismantling, D&D as an acronym there, in the Fukushima side. So just identifying where the highest radioactive fields might be and where the restriction might be to human intervention there. And at the same time, we are, of course, reviewing the accident management according to what we've seen there. And one important thing, through all the work, we have enhanced so much our analytical tools. And I'll come to that at the end of the presentation. So, in the end, both by practical implementation of new systems and by enhancing the tools, the analytical tools we are using, we are making our plants safer. And all this work has been ongoing within the OECD framework through several projects that I will mention later on in more detail. So let me talk a bit about the forensic analysis, or what we call forensic analysis, but let me first just to get a snapshot of how the site is at this time. First, there were 6 units, for those who are not familiar with the accident, 6 units on site, Unit 5 and Unit 6, they were in maintenance, no trouble on those 2 plants. But in unit number 4 and unit number 3, there were, unit number 4, there were plenty of spent nuclear fuel in the spent nuclear fuel pool, and they remove it, as you can read in here, in December 2014. Then the spent nuclear fuel in unit pool in unit number 3 was removed just a few years ago, and nowadays they are doing all the working stuff just to remove all the debris at the upper part of the building in unit number 1 and unit number 2. Of course, all of them under cold shutdown. And this is what we call forensic analysis. That essentially means that what we got is target variables. What we call their target variables is the data that we got as early data quite after the accident, that were essentially the pressure within the reactor pressure vessel, the recording on site, and the pressure in containment. Of course, in a discontinuous way. Just remember, this was a full station blackout accident. So we got just 2 sources of information to build up the whole crime scenario, so to call it, of the accident. But in order to feed our codes, our analytical tools, we need the boundary conditions. And we really don't know what systems were operating as cooling system operation. We don't know about the potential leaks between the reactor pressure vessel or from the containment, primary containment vessel, and we don't know even. Remember that this is boiling water reactor technology with large suppression pools. What is the thermal status of the pool? Because if it is saturated, this changed quite a bit the scenario. So there were so many boundary conditions that we didn't have a clue of at the beginning of our analysis. So we started building our postulated scenarios just to fit with those target variables that you could read there. And when I talk about the late data, this means that once after a few years, we started to get additional data like those rates in the reactor building or new measurements, sampling, and those data have been integrated. And here it comes where our forensic and our analytical tools have experienced a so big change. Before Fukushima, if you ask anyone to do a civil action analysis for a PSA study, well, I'd say that they will calculate a couple of days. 48, well, the most generous ones, maybe 72 hours, no more than that. Running a civil action code for 72 hours is quite a challenge. In civil action, there are processes that are so fast, while others are so slow. Processes that are ongoing over 2,500 degrees, and processes that are ongoing at 100 or 150 degrees. And you need to solve all those equations all together. So it was really hard. I can tell you that after the second phase of the BSAF project, we were capable of running our analytical tools for 3 weeks in a row. Because for 3 weeks in a row, there were some phenomena ongoing, either in the reactor pressure vessels or in the primary containment vessels. And this is what we've learned with our forensic analysis. You got all the things there listed. I won't go one by one there, but I want to spend a minute in some of them, those who are more I'd say, more representative of what the forensic analysis brought into the understanding. For instance, in unit number 1, I remember when we discussed with TEPCO people who, of course, they were always willing to share their data, they provided us with the injection rate in the unit number 1. And they gave us a schedule and flow rate, and this brought us to a full different picture of the data recorded. So the analyst said, well, it's no way that you injected water at that time with the data that you have for the RPV pressure. And then what happened is that they confirmed that that water came out from the fire truck and was injected in the plant. However, it never got to the reactor, neither to the primary containment vessel. He went somewhere else. So the first water injection, massive water injection, happened 10 days after, and this was first found out by our analytical studies. Then in the second unit, we predicted, we did our first calculations, and we predicted a pressurization rate in the containment that was much sharper than what they recorded. You know, heat transfer correlations have been known for quite many years. So it had to get some so high differences. We were very certain that the 20-30% uncertainty or error in our heat traffic correlation, but no more than that. But according to data, the pressurization rate was, the difference with the pressurization rate meant much higher differences in temperature. So we came up with the intention to how to increase the heat transfer coefficient. So we did so. We imposed so in our analytical tools, and we came up with the idea that somehow something happened that cooled down the containment much faster or much faster than expected. And what happened is that after a couple of meetings, our TEPCO colleagues came and say, you were right, because in the unit number 2, the seawater flooded the basement of the reactor building. And this was the reason why the heat transfer coefficient was much higher. The heat removal was much higher. So I could give you some more examples like that, but it's just to, for you to realize that this analytical understanding is quite important. And in the unit number 3, the most significant one was, in unit number 3 was operating when the tsunami came into the plant. But unit number 4 was not. However, there was a hydrogen explosion in the reactor building unit number 4. And I remember the times at which we spent quite long calculations just to try to justify what could be the source of the combustible gas that made the unit 4 exploding. And after a while, just justifying that it was impossible to generate radiolytically that hydrogen or by chemical reactions, we just came up with the explanation. As you can see in the center picture, unit number 4 is the one at top. Unit number 3 is right there. Unit number 4 is right at our side. There is a joint piping there going to the common chimney of the standby gas treatment. And then what happened is that the explosion of hydrogen in unit number 3 pushed gases in the unit number 4 reactor building through this T-junction and made it an explosion in unit number 4. And this was also confirmed with our forensic analysis. This is just a few plots for you with the references for you to check if you are starving for more information. I'll be happy, I'll be around here, so I'll be happy to answer any question that you may have. And we cross it also with the predictions, with the measurements of the dose rates outside the plant, just identifying when our codes were predicting those releases of fission products, and we at least identify the sources from unit by unit along the time. This is the current status, and in global terms, we match it with our forensic analysis what the TEPCO people afterwards have measured. Essentially, the unit number 1, most of the core was melted down and is in the reactor cavity. Much less of that in unit number 2, with less interaction of these hot materials in the pedestal of the unit, and in between in the case of unit 3. So neither everything nor the amount in unit number 2, just in the middle. And this is a table with those late data that came after that confirm some of the insight that we gained with our forensic analysis, just for you to have it. One example of those data, well, one of the things that we did was to cross the measurements on the left-hand side, the measurements of temperatures in the reactor core at different locations, how they decrease with time, and crossing that with the immune tomographies that we are taking just to confirm that in unit number 1, there is no any fuel remaining, practically no any fuel remaining, meaning that everything has gone into the pedestal, while the other 2 are in a different status. And the ongoing investigation is, of course, targeting those things that we don't understand. We know that we don't understand. One of them is the late phase of the core relocation, when the molten materials move within the reactor. And we know that as well because we had to fit our codes just by stating at what times and how much core materials, lump of molten materials, just slump into the bottom head to reproduce the pressure peaks in the reactor pressure vessel. But we did so ad hoc. So there is no good model for the late phase. Even for the combustible gases, you'll see in the next slide, you'll see pictures of those. How different the explosion in unit number 1 was from unit number 3. And we still have to explain that. Then the melt spreading and the molten core concrete interaction. You'll see what our codes do today and how the things look like in unit number 1, for instance. And then the fission products move up and down. But the most important thing that you are gonna hear me talking about is we need to know the mechanisms to fail the barriers of the defense in depth concept. So the reactor pressure vessel failure modes, the containment leaks, and of course, most important than anything else, those uncertainties in the boundary condition, what was the actual flow rates coming in, where the temperatures that those materials getting in were at the time of injection. These sort of things are helping us. So just for you to have snapshots of the pedestal in unit number 1, 2, and 3. This is how they look like. Just look at the center plot. This is the top of a fuel assembly handling. You know, in our codes, in order to get any material from the reactor pressure vessel to the pedestal, we need to molten them all and go in there, thermal damaging the bottom of the reactor pressure vessel, and in molten or debris status, move down to the pedestal. Impossible to have that piece going through. This meant that a big hole appeared there at any time during the accident that our codes, such as they are written today, are incapable to predict. And this is why in project like Takeoff or Takeoff 2, we are looking at the structural materials and the ternary systems that might form, because it might be the case that a hole might open at some point, and this is just a hypothesis, and let some material going through, and then their own mixtures of materials of tactics can form and clog the whole form. And coming to the MCCI and the spreading, you know, in the central part of the slide is how we predicted that the interaction of hot molten material with concrete is gonna evolve a long time. And this is the erosion depth. So in the 21 days that I mentioned before, we predicted continuous degradation and erosion of the concrete slab. But observations told us that no way. After a few days, that interaction really cooled down and stopped it. But our codes couldn't predict that. And nowadays, after those forensic analyses that were kept on the ARC-F project, we found out that when you go over few days of this interaction, it's very important to consider the thermal conductivity through the concrete, because at those times the decay heat has lowered so much that this conduction through the concrete becomes important then. So we've already tested that by introducing the thermal conductivity of the concrete, we go to the steady state that was observed. But what is still impossible to explain is the cavity, what you are seeing on the picture on your right-hand side. That cavity, so essentially meaning that there is no concrete around rebars, and the rebars are just intact, not brand new, but mostly intact. And we don't have any explanation for that either. We are working on that. But in our code, there are no models that can explain so. And this is what I said before, coming to the explosion in unit number 1 and explosion in unit number 3. In unit number 1 is a kind of flat explosion, white color. Unit number 3, you see, is much more vertical, two-stage explosion, and well, in here you don't see clearly, but with a kind of orange color as well. So they were different. And now we've got hypotheses to explain these differences, but still to be proved. We got two options to explain it. And then coming to the leaks. You know, let me give you an example how important to know the leaking things are. When you come to our models, and we are researchers, so we love sophisticated models, CFD or lamp parameter code, never mind. We like a lot of sophistication in our modeling. Problem is that it comes to a point where your model might be as good as you want, but if you don't know the boundary condition, you get lost. And the boundary condition comes so important that in unit number 1, if we assume just a small little leaky between RPV and the PCV, that is much more important than any uncertainty you might have in the pool scrubbing modeling of the suppression pool. So let me come to the lessons learned. Because so far, if you crystallize those insights that we gain, what the things that are still ongoing, we got something there. First lesson to learn. In our reactors, in the running reactors, C reactions is highly unlikely, no doubt, but it's still possible. And we should, and this comes from my side, nuclear technologies should be ready as they were going to happen right in the next minute. And this brings education and training onto place. So just looking at the whole thing, one of the major points made has been how important it is the independency between the regulatory body and the nuclear industry. The perception of challenges. If I can share with you how we lived in Spain, those sites with a couple of reactors, if you go there and you discuss before Fukushima, you know, you have 2 reactors, they say, yeah, so if I got a C reaction in one of those reactors, all the equipment in the other reactor will help them. Well, this is if the threat does not come from outside and you have both of the units undergoing an accident. So just the potential of external hazard, the multi-unit sites, the whole concept has changed. And we put so much care in mitigation and prevention. Just to recall you, passive photocatalytic recombiners in those plants that were not installed in Europe have been installed all the way through through our nuclear power plants, or venting passive filter containment venting systems. It is very important, and I didn't mention that in unit number 2, the reactor was cooled for nearly 3 days without any safety injection, just with a system that was there for shutdown operation. The RCCI, the R6 system, was capable of working off nominal conditions and providing good cooling of the unit number 2 reactor. So I think I can skip this. I already said so in some of the previous slides, but the impacts that are happening after Fukushima goes in very many layers. So from safety culture to a specific phenomenology that you can read there, going through a rethinking of the risk assessment methods and accident management guidelines. To me, and this is controversial, not everyone has the same opinion, what we've seen as a water management in Fukushima was exemplary. I mean, they kind of faced with a challenge never expected of the amount of water, and they handled that in a so good way. And also, with Fukushima, of course, some technology is being developed. I'm talking about robots that they are building just to withstand high radiation fields, some of them flying, some of them moving around, some of them diving in pools, just to grab samples and take those samples for the analysis and provide further data for us to keep on consolidating the scenario that I mentioned in the previous slides. And this is all what I got for you today. Thank you for your attention. You.
Okay. Thank you very much to both speakers. We have now quarter of an hour for discussion. We are a little bit late, but I think we had two very interesting presentations, and I do not want to make the debate shorter than questions?
There's one.
Yeah, there is one.
It's coming.
Coming.
Thank you very much for the presentations. I would like to ask Professor Luis, is there any report on the molten fuel lump at the bottom of the Fukushima achieved actually criticality there? Is there any measurement that does that lump of fuel achieve criticality or approach criticality? Thank you.
Well, I think I can use this. Well, no at all. I mean, in those slumps of multi-material that I mentioned, of falling into the lower plane of the reactor pressure vessel, there has not been a spike in reactivity that can justify the pressure that have been experienced according to the data we got. What is more dependent than the criticality there is on the amount of the materials falling into the bottom of the RPV. So no criticality signature so far that has been reported.
Thank you. Yeah.
Hello.
Third line.
I would like to ask a question about pyrochemical reprocessing of the fuel in molten salt reactor. Could you explain maybe more in detail how the fusion products are removed from the fuel? Do you consider some kind of material for fusion products ionization or electrochemical disposal? I'm really interested in how you online can reprocess the fuel and remove the fusion products. Thank you.
Yes, there's critically important technology to demonstrate the molten salt space reactor I discussed today. There are three kinds of fission product, as you understand. Noble gas, easy. Noble metal, relatively easy. We do have helium bubbling and argon bubbling. Problem is, what challenges are with the soluble fission product. About 50% of fission product are soluble. Fortunately, we do have electrochemical separation, just like a pyroprocess. Well, so to make it short, we need development, some new technology to effectively remove soluble fission product. But again, I believe there are some basic technologies.
Thank you so much for the very interesting presentations. The first one regarding It's more technological, let's say, and the second for forensic study. Actually, I'm asking what about the measures of both, let's say, directions, but what about the measures of the nuclear security, even for after the forensic study or analysis? And also, what about the new technologies regarding the salt molten or the fast reactors? What about the measures of, because I'm speaking about from the perspective of the nuclear security, as long as I'm a member of International Nuclear Security Education Network, IAEA. Thank you.
You may go first.
Okay. So, as you are familiar with the security, so probably you know better than me. The forensic analysis that we've done has nothing to do with security at all. It's just safety. How much this changed after Fukushima, I think that is a consequence of a global reflection. You know that there has been an evolution of security measures in different countries, different ways, but has been an outcome of the reflection after the Fukushima accident, combined with all these severe things that we've been suffering in different sectors, fortunately. But it has been a reflection outcome, nothing specific coming out from Fukushima.
Well, regarding the security and safeguard of, the molten salt perspective with the closed fuel cycle in online, something like a pilot process, it's a big issue. So I have to say, there's a long way and quite challenging way to go regarding that issue, but there's no free lunch. So we have to develop much safer and more proliferation resistance, technologies for sustainable nuclear. So if we pay for that, we may get some return. Otherwise, I think we have, again, always worry about Fukushima like severe accident. That is my short answer. Yeah.
Okay. We have one here in the first line row.
So thank you very much for the very interesting presentation. So we had a presentation where we had a severe accident-free type of reactor, and from the other side, a severe accident. So it would be nice you can comment, both the speakers, about the definition of severe accident for advanced reactor. Is it a severe accident-free reactor because the definition does not apply to your reactor, the current ones? So it would be nice to see what, in place of saying severe accident-free, what is a severe accident for advanced technologies? And I would like a comment from both of the speakers, if it is possible. Thank you so much.
So we are running out of time, so very simply. Some molten salt reactor people claim there is no severe accident at all in the molten salt reactor design, and people are working on it, but I believe there could be some chance of be concerned when a lot of liquid salt spill out into the environment. Although it cannot be as serious as in the conventional reactor. So people are working on it. There's no clear definition of the severe accident in the molten salt reactor at the moment. Yes.
Okay.
Well, Martina knows what she is asking, of course. I'll give my personal opinion of what that severe accident goes on. Is under keeping the control where the fission products are located. When you lose the control of the fission product location, you are in trouble because you are not controlling what is damaging outside. So for the current reactors, it's very unlikely, but it still might be possible. For those AMRs or SMRs that claim not to be physically possible to undergo a severe reaction, so to lose control of fission products, is fantastic. They just need to prove it, but it's fantastic. And just remember that something that we thought was impossible already happened. So by proving that it's impossible to lose control of the fission products in the system, I'll be happy to say they are CV reaction free.
Thank you. Yeah. There's a...
Yeah. Thank you both for your presentations. Perhaps that will be a good question for closing, since I see Dr. Afak is waving. My question is to Dr. Luis. So yesterday you gave a very nice comment to the panel, and you said to better a better sentence for the theme would be lead the innovation through preservation. In that sense, do you think that innovation should be centered around such real data from the 5 accidents or 3 accidents that you mentioned, or is it something not to be overlooked? However, innovation should, let's say, for the sake of efficiency and not only for the sake of not repeating the mistakes. Thank you.
Well, thank you for that question. Quite interesting question. Just my opinion, just to make it clear. One thing is not forget about the past and preserve that data, because according to how I see the nuclear technology coming, in the coming 10, 20 years, most of the reactors to be implemented will be water-cooled based. So for all those, most of the lessons at detail level can be based on what we already have from these events that are so undesirable. But from the innovation side, from the AMR, advanced modular reactors with a different approach, what is very important is to know up to what point the data that we already collected can be applicable. Let me give you an example. Some people say that fission products, the generation of fission product will be through the same reaction, eventually will exist and all that. For the fission product transport, in case they move outside any primary barrier, the models that we've produced along these years in the light water reactor technology are applicable to a good extent. So we have to take advantage of the knowledge already gathered to help innovation to go faster in those sites where they need to be really innovative. But if there is no any need to reinvent the wheel at those points that we already understand.
Okay, I would be very glad to continue with this interesting debate, but Dr. Afak Shams is not looking very nice. So at this point, I have to stop the debate. And I want to say thanks again to both speakers for very nice presentations, and thanks to the audience who contributed with their questions.